Welcome to an exciting lecture series of the Institute. I really welcome to my friend and colleague in this field. I mean, we are working from last 2 years together, and Dr. Mohammad Ramzan, he traveled all the way from Germany on my invitation to share his expertise and knowledge, which has, in principle, did his bachelor from the Punjab University. So this is our own product. And then he left to the Korea, South Korea. He did FBS from MS from there, and then moved to the Germany. And he has a quite good experience from a different institute of Germany, including Leipzig, and then Orlando, and then recently Vienna University. He's working from last 6, 7. Basically, currently he is doing his habilitation in physics, material physics. So he's going to be share his expertise in this field, and we are going to be. So today we have the one lecture, and then from tomorrow we are going to start almost 1 week of hand-on experience, a workshop. So probably few of you are going to be participate in the workshop. So I formally invite Hamzan for you. Thank you very much.
Okay, welcome everybody. Thank you for the kind introduction, and it's my pleasure to be here finally in Pakistan presenting my work here. And as you know from the title, today we will be talking about 2D materials and their potential application and some devices made out of them. As you can see already that, and I will also explain in the following slide that we have recently, actually starting from this month, when I was in Pakistan, I virtually moved to another place, like 400 kilometers apart in Germany. But okay, so let's get started. So, quick overview of the agenda for today's talk. As one of the reasons for being here is to bridge some collaboration between our group and the group of Professor Zahir as well as some other potential collaborators. So I will start with some introduction that would be not only just scientific but also non-scientific about myself and our group. And then there will be two parts. The talk is divided into two parts. The first part is about a class of material, which was actually, I started my PhD studying that class, and it's a hypothetical class. So we have explored the potential existence of this class of material, and then we see if we could exfoliate monolayer or bilayer from those materials and what are their potential applications. And the second part will be about the potential application of this class. And one of the material SMP3, you will see a lot of time with SMP3. I will also give you a short introduction of this class of material and specifically why we choose that material. And then in this study we found a special feature in this class which is called negative differential resistance. So I will explain you that what that means and why it is important. It's a bit uncommon to see such kind of. And eventually, I prepared one slide where I will take you through some of our recent published work. So to give you an overview, like what potential collaboration we could have, what expertise you could expect from our group. Okay, so as already Dr. Zahid introduced, I did my bachelor's from Punjab University, and then in 2015 I moved to Korea with the hope to do my PhD and come back, but unfortunately so far did not happen for some personal reasons. But anyway, so you could see here I moved to this university, which back then was called Jacobs or Jacobs University to pronounce it in German. And now, if you search for it, you will find actually the Constructor University. It's renamed after the investors who bought that university. It's a private university there. And there I started there as a researcher in the group of Thomas Heine. You will see in the background this guy because this was like the fresh after post-corona defense. I was very happy that I could do it in person because you roast yourself for several years, and then I feel very bad for people who are doing it just online. But I was happy I could celebrate it in person with my group and my family and friends there. So and but I was directly supervised, or I was first PhD student of Dr. Agnieszka Puch, who is working for past several years in the group of Thomas Heine, and she did habilitation during my PhD. So now she's so just a background for those who don't know habilitation. So it's like a certification that you need to teach in the university in Germany. And in a way, this is a certificate you require to be a professor there. So yeah, their things are a bit complex and difficult to be a professor, and that's what I will be doing. So right after finishing my PhD, I started the group EST group as a postdoc, and until last month, we were in Oldenburg, and now we have moved to Jena, a very nice town in the valley in the east of Germany. And so what is EST? EST stands for Electronic Structure Theory, which explains essentially what we do. And it's a group led by Professor Katrina Kopi. And here you have a glimpse of all the students we have here. Unfortunately, there are several new faces that I could not include, including some of my students. But what important message this slide could give you is that though we are based in Germany, but our composition is very diverse, and I'm very happy and proud to be part of such a group with such diversity. Okay, so I was not aware, to be honest, about the composition of my audience, so I prepared one slide to give a slight, let's say, background or a feeling of what we do. And in principle, we do first principle, or you can also call ab initio simulation based on DFT. Ab initio is the Latin word, which literally means from the scratch, meaning the only input parameters that we need is the position and the nature of the atoms. So the position is the XYZ coordinates, and then the nature, what each element is. And then essentially we solve a Schrodinger-like equation, which looks like something like that. Here you see, yeah, yeah, yes. So essentially here we have the Hamiltonian, which has this term stands for the kinetic energy of the electron and the effective potential, and then the orbital of electrons and their corresponding eigenvalues, the energy of orbitals. And essentially, this effective potential consists of three terms. The first is about the external potential that is there due to the presence of nuclei. And then the Hartree potential, the electrostatic interaction between the electrons. And then this third term, which includes all the exchange correlation terms. So I put it in the red because this field has been used a lot, but there is a limitation that this term, we don't know this term analytically. So we have to make always approximations. And what we get are what we want to get depends a lot on those approximations. So if some of you know this background, so you might have heard a lot LDA, GGA, all those approximations. So they are for these terms. And for those of you, oh, thank you. For those of you who might know already, but for the new audience, I would like to give a recap of what we essentially do. So it's a self-consistent problem. So essentially, what we do, as the name says, it's a density functional. So we guess the density, the distribution of electron in our system based on their position, and then we calculate this effective potential, and then we update our Hamiltonian, and then we calculate. Sorry. Yeah. So then we recalculate this electron density. So we update that, and then we reevaluate. So and then the essential purpose here is to converge to go to the minimum. So the energy and the forces they should be as minimum as possible. And based on our set threshold, we consider that we got the true ground state density. So essentially, this is let's say the dough for your cake that has to be there. And on top, whatever you build, it depends on your field or what you want to calculate. For example, if you want to calculate the optical properties, then you do go for many body approximations. And if you want to calculate the transport properties, from here we go further to the non-equilibrium screen function, and that's what I will show you shortly. And just 1 minute. Yeah, sorry. So essentially, now till now, with this theory, we got the true ground state density. And without going into details, because I know that it's a chemistry and biological department, so I don't want to afraid my audience with very many scary equations. But I would like to just give you one equation which shows that essentially from that ground state density, we calculate the retarded Green's function, overlap matrices, and Hamiltonian for our new system, which is open system, because now we have, if you know the device for which we will calculate the transmission. So essentially, you have two electrodes and a scattering region in between. So the transmission is that the electron goes from left terminal to the right terminal. The current flows through the system. So there you need actually three parts of your system. So you need left, right, and the scattering region. So for that, you need to build a modified Hamiltonian. But essentially, you get at the end energy and voltage-based transmission through your system, which you could further, using this lambda optical formula, you could get the IV curve, the potential base front going through your system by simply integrating all the states that are in your bias window. So now I would like to give here a small hint that this part of work is highlighted in gray because this is not really expertise of our group. This is something that I did during my PhD in collaboration with my former mentor. She's now a professor in South Korea. So, but this is something we are further expanding in our research portfolio. But what we essentially do is actually we calculate light matter interaction, and for that we do static as well as dynamical calculation, the real time dependent DFT. What I explained, it's a one extended version of DFT, what I explained as a base of our. So, and then we study a big class of materials. So one class is actually perovskites, which we are also in collaboration with Dr. Zaheer. But furthermore, we also study organic molecules and their crystals, as well as we also study inorganic crystals. So we study their electronic properties, as well as we see the excitation of electron and its dynamics under the irradiation of laser. So it's more like an optic field. Yeah. And we also study the hybrid. So the hybrid is you take one layer, the 2D layer from this inorganic material, and take one organic molecule. So you mix this so-called HEOS, the hybrid interface between these two materials, and see the response of your system under different laser excitation. And last but not least, we have high throughput studies where we actually look for new materials and the phases of some existing material for different applications for energy storage and okay, so now we can switch the gear and go to the scientific part. And as my audience might be aware already that the all started in the 2D material, the low dimensional material started with the discovery of graphene back few years back. And by now, in the last decade, we have actually a bunch of different classes of material, ranging from metallic to semi-metal to semiconductor as well as insulator. So it has gone a very diverse field of research, but you could divide it simply into two classes, which I try to explain here. So essentially you have bulk materials, just like graphene, as you know, it's from the graphite, which is essentially the lead pencil that everybody uses every day. So essentially it's a if you look at the very nano scale of your pencil, so essentially it's like the layers of graphene that you see in the middle stacked into different fashion. But for the reference, what we see here is not graphite or anything else. It's a bulk of this SMP3, the class that I will be introducing. So and then you pile one layer from these several stack of the layers. essentially. So it's called Scotch tape method. So because this is how graphene was exfoliated, that they keep on exfoliating layer of with the tape of with the Scotch tape until they got the mono layer of that. And another name is also the top to bottom approach. So you have layers stacked, many layers, and you go till the bottom to get one layer. So this is how they characterize. More recently, we have also studied a class of material which was actually published in 2021. This class of material which does not have any parent bulk. So you don't have like we see on the top. So they are actually grown material. So it's called, that's why it's called bottom to top approach for such kind of material. I will give you a small overview of this material because we are actively studying this class of material as well. So now to the results part. So as I explained a couple of minutes ago, that we have bulk, which is stacked of several layers in this A, B, C fashion. And essentially, if you see from the top, it's like a graphene, so hexagonal pattern, but each stacking atom is from a different periodic table. In graphene, sorry, you have just carbon, and here you have combination of these two. And why we studied that? Because in 1970 there was a group that successfully synthesized these two materials, SLP3 and GeP3. So they are not hypothetical. They were synthesized in the lab, but nobody looked on to them anymore. Everybody was running after graphene and MOS2, molysulfide, and so. So in our group, we first started with this GeP3, and we see if we could exfoliate monolayers from that. And when I joined the group back then in Leipzig, I was assigned to study the full class of such material. So essentially, as you see that there is a similarity of structure and the composition. The only difference is the germanium and tin atom. And if you look at the periodic table, so they are just next to each other. So then there was an obvious question that is it possible that there are a whole class of such material where you keep fix one X and substitute Y or the vice versa? So this is what I studied. So first we started with the stability. So essentially this is called polar dispersion spectrum. So this tells you all the possible vibrational modes in your system. And as you can see, the bottom is at 0. So all the vibrational frequencies are positive. So we don't see any imaginary frequencies or the negative mode in our system indicating the dynamic, the mechanical stability of our system. So next, we see if we could cleave one or two layers from that. So for that, we calculate the cleavage energy. So what cleavage energy is? So it's essentially a penalty because they are in their equilibrium form in this combination. So essentially, the cleavage energy is a penalty that one has to pay to remove one layer from its bulk or two layers from its bulk. And essentially, how theoretically we calculate, we take a bulk material, bulk-like material, several layers, and then we move it away from the rest of the material and calculate just absolute energies. And essentially, you can see that everything is below this threshold. So this threshold is like the threshold for this mechanical exfoliation, which I was explaining in this Scotch tape method. So if so in the literature, up to this, the system that has a cleavage energy up to this point have been exfoliated already with this Scotch tape method. So what we found in that the phosphorus-based compound, everything was at or below this threshold, indicating that we could easily exfoliate these layers from this Scotch tape method. Only one system, which is monolayer of silicon phosphide, is above this range, which does not mean that we cannot exfoliate, but at least not with this method, because nowadays we have also several methods where you do that chemically. So you integrate some molecule between the layers and then you exfoliate that. So this would actually target some layered material which has very strong cleavage penalty. Okay, so long story short, now we found with this that we can cleave monolayer and bilayer. Now, what about this stability? So as like we calculate the Conan spectrum for the bulk, we also calculated for the monolayers and bilayers, and we found that they are all dynamically stable. We also calculate their thermal stability by calculating their by simulating them at the room temperature. So the structure sustained, indicating their thermal stability as well. Now, what about their electronic properties? So all materials that has number of layers more than 3, they are metallic. Only if you go for one layer or two layer, some of them, they become semiconducting, indicating a strong quantum confinement effect. So as you go from top to bottom, from 3 layers to further down to one layer or two layer, you get an opening of the band gap due to the quantum confinement effect of electron in this case. However, there are still some materials based on because of their combination or composition, they are still metallic. So there you don't open the band gap. And in those materials where you see semiconducting, you already see some different colors. So it's essentially the electronic band structure, which shows the size of the electronic band gap and where it is in the reciprocal space. But in the colored shade, you will see that we have opening a much larger band gap. And this is essentially what I highlighted a few slides back, the effective potential that I marked in the red. So based on what you chose, how you approximate that effective potential, you could get a different band gap. So because the density functional theory is actually seen with the underestimation of the band gap. So, and this approximation kind of help you to achieve the band gap that your material have in the real scale. So now we have seen a class of material that is metallic in several layers, but turns into semiconductor when we thin them down to 1 or 2 layers. Now the question is what we could do with that. So what is the potential application? So the one potential application is that we build a single junction out of these materials. And what is that and why it's important, I will explain you shortly. But essentially, you have the device that I was explaining before. Yeah.
One layer material of 10 phosphide. That was also non-metallic semiconductor. The plumbum phosphide, PB phosphide, the last one.
Yes. No, it's not. It's a semiconductor.
Okay, it's 2-layer material. It's
Okay. Yeah, that I don't remember by heart, but actually in this phosphorus compound, what we have semiconductor in monolayers was also semiconductor in bilayers. But these two, they were metallic in every case. And for those also, I don't know the size of the band gap, but definitely it reduces because it's going towards metallic phase. So it has a 0.5, for example, and bilayer is 0.25, and trilayer it vanishes the gap. Yeah. Yeah.
what was the reference for energy? Fermi or BBM?
Sorry, come again.
What was the reference for energy? Y-axis.
Yeah, sorry. It should be labeled as E minus EF. So the Fermi level is set to 0, and the valence band is shifted to the Fermi level. So this way it's easier to get the estimation of the gap. Yeah.
Can you
Yeah.
to a previous slide? Yeah.
Okay. Yeah. So essentially, we have actually a dedicated session for Q&A. So you could take note. But if there's something is really puzzling you, you can stop me still. There's no problem. Yeah. Yeah. Okay. Okay. So I explained to you that we could make devices out of such materials, right? Why they are important, I will explain you shortly. But now the next natural question was, we have a zoo of different materials, so which one to choose? So we picked SNP3. The reason being, while I was working on summarizing those results, there was a collaborator of Thomas Heine who managed to exfoliate few layers of SNP3, which obviously make this as an our choice. So they managed to exfoliate SNP3 and they also show that they are ideal candidates for some battery application, the lead-free electrodes. So this was then our choice. For that, then I contacted my mentor and very good friend, Dr. Hansel Kiel. Back then, she was in senior researcher at ISTI in Beijing. There I studied my masters. And then we decided to work on that all together because she is very expert in this quantum transport simulations. She had even developed her own code, so it was very fruitful collaboration. And yeah, so essentially what you see here is actually the device that we made out of these materials. So this, what you see from now onward is actually SMT3, the sphere, like the larger sphere, actually in the purple color is tin atom, and the other one is phosphorus atom. So essentially what we did here is that we used this nature of having metallic three layers. We use it as an electrode because electrode should be rich of electrons so that it could easily go from left to right. And then the monolayer was used as an scattering region, so the channel region through which the system, through which the current passes. And then we could use it for our further purposes, for example, gas sensing. So why this is important? Because so normally when we build a device, we have electrodes made up of gold or silver or similar material, and then we connect these electrodes with a 2D layer. And since there is a lattice mismatch and composition mismatch, you have a lot of complexity at the interface. And as a complexity from an experimental point of view, but also a limitation because then you have a larger Schottky barrier that the current, the electron has to go through to pass through the channel device. And this kind of drop the current in your device essentially. So this we could avoid by constructing such kind of single junction devices. So in such study, what you simply do is, since we have, so for these studies, we have used a Siesta and Trans-Siesta code. And those of you, for example, like Repa, who knows this code, it's a localized basis set. Which will, without going into details, one takeaway from that is that in such simulations, you have to be careful what you choose as a basis set. So the benchmark is that we used for the previous study, the plane wave force. So the first step is to regenerate or reproduce what we have seen previously, which is essentially we have monolayer, which is semiconductor, and then we have bilayer, which is also semiconductor, and trilayer is metal. That's what we need. Okay, so next step. We have several positions on which we could absorb our gas molecule because we want to use this device for gas sensing application. So essentially, we have several different positions labeled differently where the molecule can sit. For example, you have CO2, you are working on CO2 gas capture. So when CO2 interact with the surface, it could either sit on top of tin based on if it loves the electron or if it hates the electron, or it would sit on the phosphorus atom on top of it, or in the hexagon made up of these two different atoms, or a hexagon which is only made up of phosphorus atom. This really depends on the nature of your gas molecules you're working with. But essentially what we do is we calculate the absorption strength of each molecule on these different positions. And what you see here on the top is all those molecules, the names are on the top, where they prefer to sit on our substrate and what would be their interlayer distance. And based on their absorption strength, we simplified it as making two groups. The type A, which binds weakly to the substrate, and then the type B, which strongly binds to the surface. And below you will see the charge density difference, which is the result of absorption of your gas molecule, which indicates in total if it took the electrons from the surface or if it denoted based on the color code. Yeah. So now we have seen that we have two classes, two groups of our gas molecules. So now next we calculate the IV curve. So this is essentially what we The top is for the weakly bounded molecules, which is very, let's say, um, um, a naive approach, or let's say a famous quote by one of very famous politicians from this part of the Pakistan. The more voltage you have, the more current will be there, right? So I shouldn't be saying political, but it's a nice quote, right? I'm being politically unbiased. I use that quote. So essentially, what happens that as you increase the bias voltage, the more and more current passes through your devices, right? So this is like the typical or the custom way that people observe, and each color code represents each molecule that was absorbed on our device, right? But the peculiar behavior we notice when we absorb the N molecule. For NO2, it's somewhat similar, though the increase in current is not as high as we see in the other molecules. But essentially, what we notice here is so to say negative differential resistance, that you increase the current up to a critical value, and further increasing current, instead of increasing the current, it drops the voltage, and then it starts increasing again. So this is not really, so to say, something that I found for the first time. Would have been great if I did that, but this already exists in the literature. So they named it as negative differential resistance. So it's let's say not known for all materials. So what we essentially see now here, that type B molecules have significant change on the transmission of our device. So sorry, I forgot to mention that this gray, I don't know if you can see on this color contrast, but the gray one here is the device, the pristine device transmission. So you can see that the CO2 has very similar or no effect, but the other two molecules have significant, even in this case. And for this NO2 case, we notice this negative differential resistance in our device. So in this study, we also wanted to understand, okay, this is something which exists in the presence of this molecule in our device, but we cannot say why this material is showing that, but we could try to understand what is happening in that material in the presence of this molecule, right? So for that, sorry, before I show you those scaling plots, so essentially what we target here is a base, let's say value, the base voltage, where it's behaving as it should, and then the peak of this curve, let's say the peak point, and then a valley point, and essentially we try to look into the structure of the system, what is happening in these 3 points. And what you see here is essentially the transmission curve highlighted by the bias window. So essentially, as I was trying to explain on the method slide, that for the current is actually an integration of all the states that are inside the bias window, right? So, and how large the bias window depends on your voltage. And as you can see here, from this small voltage, you have a small window which shows that if you look at the real space of this state, the electronic structure of the real space, you will see that essentially the states are localized on left and right electrode as it should be. And there are some small probability of passing the current, and that's why you see small increase, right? So far so good. And then here we have some states which are actually molecule induced states. What happens when we slightly increase the voltage? This voltage split those states into two. And one of those states is inside our bias window. And that shows in the real space that this is a very rich or metallic state. So it is all over the device. So that's why the current is much high on that point. What happens then when we further increase it, so this further voltage pushes this other state, which is very metallic, but it pushes it away. So it's not inside our bias window. The state which is the voltage actually breaks some of those states. So it's not as metallic as it was in the case of this beta state. So That's explains what is happening inside the device when we see this law. This was very nice work that we found, and we publish it into NPJ Computational Materials. So if you are interested into it further, just have a look on that publication. Okay, so I don't know. I did not notice the time. Probably I'm okay. So yeah. So yeah, just now one slide about our current research directions in case somebody is interested to collaborate. We are just an email away. Just feel free to write us. Yeah. So as I was saying, we are recently studying this new class of material. One of the members of this material was synthesized in 2021, which is MOSI2 and 4. And we have actually two publications on this study where we, similar to what I did in the start of my PhD, this was right at the time when I was finishing my PhD. So we have two papers, one published in small and one published in recently last year. So you can have a look on those materials. These materials are very interesting for several reasons. Unfortunately, due to the constraint of time, I could not cover that, but I will left a QR at the end for our Google Scholar, my group, so you can have a look on that. But essentially, this is the material we have been studying very actively recently. And then some of my very first remote internee from India, she was working on this project where we looked for a material who had the lattice constant matched perfectly with the very famous guy MOS2 in the community. And so essentially what we get here is actually a van der Waals heterostructure which does not have an intrinsic strain. So strain is actually can change a lot of properties in your material. So even there is a dedicated terminology for that, strain tronics. So, so in this combination, we could have actually properties that are mainly driven by the van der Waals interface between these two layers and no contamination coming from the strain. This work is already published, I think, in ACS Omega. You can also have a look at that. What I've been also doing a lot during my PhD and more recently also studying the van der Waals heterostructure of TMDC, this transition metal glycogenide. So here we have actually intrinsic strain. What does this mean? Is that, for example, if you take tungsten diselenide, it has a smaller lattice constant compared to molybdenum. And MOS2, the famous guy, has even smaller lattice constant than tungsten diselenide. So essentially, when we stack them together, so now there is this competition of which material should be in its relaxed position. Because if you average them, then they are both at the strain. So in this case, I had another study during my PhD where we introduced a two-step approach. So I wish I could introduce that, but I could give you one liner of this approach is that it's a cost-effective and efficient way to simulate such materials, which is, in a one nutshell, that you divide your simulation into two steps. So in one step, you distribute or you shift the strain onto one layer. And in the other step, you shift it to the other layer. So in a way, you have the presence of this van der Waals hetero interface in your system, but one of your layer is relaxed. And then you could look at the states or the electronic structure. From the electronic structure, you can look at the states if conduction states are being formed by this layer. So in a way, when you are relaxing that material, then only in your electronic structure, these states are relevant, or these are like, let's say, the better represented states, and the vice versa. So, so here is the paper that we published in 22. So you can have a look at that. Yeah, with this, I would like to summarize what we did. Essentially, we studied this. I represented here the bulk class of material, which has the potential to be cleaved, and the cleaved monolayers they have a variety of electronic properties, which shows a potential to be used for electronic devices, which we also studied, where we have tri-layer electrodes and a single layer as a channel region. And this device shows us this negative differential resistance, and this is ideal for sensing the NO-based gases. Okay, with this, I would like to just give you the Google Scholar QR code. If you are interested, you could look all the publications that I have presented and most recent work into my Google profile. And with this, I would like to thanks all the funding resources and our group, and now stay open for any questions. Yeah.
Was very clear to me, the person.
Yeah, I hope the
I'm from a physics background.
yeah, the non-physics people share the opinion. It will be success for me. Yeah. Yeah.
And that very the length of the base of your transistor.
Um, Let me recall. I think yes. So we
Did you
stick.
find any changes in current?
Actually, as you were saying before I started my presentation, that these are very expensive calculations. So, and this IV curve, the current things that come quite late. So what we conversed with was with the transmission. So back then we changed the length of this the channel region and looked at the transmission curve. And by the time it was constant or unchanged, we stick to that. Then.
Second question. You did mention sensitivity of this.
Yeah, that's a good question, actually. Yeah.
But it must work with very low base voltage, right?
Yes. And indeed, this is the case. Sorry. Let me switch. I don't know what was the slide number. Oh, no. Other slide, sorry. Okay. Yeah. So you see that the main observation for these nitrogen based, so that's why the title of the paper was also based on nitrogen based gases. Because at the heart EV, you could already detect NO very clearly. But it's not, I must admit that it's not good for the other molecules. But at least for this nitrogen, that's why we also named it like that. Yeah, please. Thank you so much.
Okay, projection. Theoretical or experimental or both?
All my
If
PhD.
you are talking about preparing this online, I think you that very easy.
No, I don't. I mean, I do all the theory. This other project where the SFP3 was exfoliated, it was done by some collaborators.
What this measure about this current diagram? Theoretical.
Yeah, this is purely theoretical. But as I was saying before, that we choose this material because it's have been already exfoliated. And since it was very fresh back then, so the only application they studied was for the battery storage, the battery related, which shows a great potential of this material there as well. So, but this device thing is very in that sense.
The first before this, right? About this figure, what type the forces that make only some like this gases can absorb the materials. Physical.
Yes.
Why?
Yes.
What type of this force?
Yes, so so just briefly the question for the online audience as well. So your question is that what are the forces between these gas molecules and the substrate, right? So we just calculate the absorption strength. So as you can already see from these side views, none of this absorbed physically onto the substrate. Only this material for this case, where the NO base was, but still I would say the strength is in the range where people will designate it as chemisorption, that's probably what you meant. But as you can see, that this is sitting in the hexagon, and it's not really attached to any molecule, but it's really packed into this one. So
a catalyst.
I think so. Yeah. To be honest, I was even this work was delayed because I was summarizing my PhD. So we published it after I defended my thesis. But if it would have been done on time, and I was not disappointed with the prolongation, I was even thinking to study. As you can see, that this as people are studying CO2 capture, this seems to be a very nice platform to capture the NO molecule. So these are the hazardous gas molecules which many industries, urea-based industries, several industries are producing. So this seems to be a very nice candidate to study such kind of capturing. Maybe you can check quickly if there is a question in mind. On the phone. Yeah, when you don't get any question, it means either you presented it very well or nobody understand anything. So I don't know which one is the case,
but I still appreciate for the audience.
yeah, really.
We are moving from one direction. But you can check it. Okay.
So as Dr. Zahir said in the beginning, I will be here for a week. So if you feel like you see some potential overlap, just reach me out. I will be, I don't know sitting where, but probably in this group somewhere.
I really appreciate.
Yeah.
So I want to say that this is just the beginning of the area of research in our institute. So we are trying to move towards the material science, and a lot of people are already working.
Yeah.
In a different direction. I mean, we have the experimental group. We have just starting with the experimental group, theoretical group. So I think we need some couple of years more,
Yeah.
and we can be established in this area. Probably, as you know, this institute is really well known in terms of natural product chemistry, protein chemistry,
Yeah.
and stem cells, and some other branches of biochemistry. Recently, we established in other branches. This is one of the branches established in material science. And the collaboration with Germany's Institute, which is particularly, I'm really thankful to you and Katrina for providing this opportunity to establish. With this collaboration, I'm quite hopeful that in near future, not only my group, but other groups will also take participate and get the benefit. And this is the way science basically, evolve, and then we move forward. So thank you very much with this. And I appreciate for all the audience, and I'm expecting that we will have the opportunity to contact with him. He will be stay with us for 1 week. So if you have any more interest, you can always come and visit. Thank you.
Thank you very much.
Thank you.
Yep.
जैसे अगर हम यहाँ पे कोलैबोरेशन कोशिश करें, मैं किसी भी डिपार्टमेंट से मटेरियल साइंस पे काम करना चाहता हूँ।